So hi all, thank you for being here to our fifth CosmoVerse online training series session with Dr. Matteo Martinelli. Thank you, Matteo, for accepting our invitation today. CosmoVerse, as you may know, is a network of over 400 researchers in Europe and over 600 globally, with the aim of unifying efforts in confronting the question of cosmological tensions and understanding how different parts of physics can contribute to that effort. Dr. Matteo Martinelli is currently a fixed-term researcher in INAF, Osservatorio Astronomico di Roma. He obtained his PhD from Sapienza University of Rome under the supervision of Professor Alessandro Melchiorri in 2012. He has been a postdoctoral research fellow at SISSA in Trieste, Italy, a postdoctoral research fellow at the Institute for Theoretical Physics in Heidelberg, Germany. He then served as an ITP fellow at the Lorentz Institute for Theoretical Physics in Leiden, Netherlands. Then he held a junior leader fellowship from La Caixa Foundation at the Institute for Theoretical Physics in Madrid, Spain. Matteo has mentored over 15 students and has been awarded several networking and research grants. Matteo's research interests span different theoretical and observational aspects of dark energy and modified gravity, and in this training session, he will focus on model-independent deviations from general relativity, covering both theoretical and phenomenological aspects. Matteo, please start in your own time.
Thank you, William. So, welcome everybody for online presence, since I'm getting this lecture from the theoretical cosmology course. Just a couple of organizational things. We are going to have a double lecture. The first part, we will talk about modified gravity cosmology, will be a quick overview. We will take a short break after that, and then we move to Bayesian statistics and how we can demonstrate these weird models with observations. So let's start from the part of modified gravity. What I want to talk about is models that we usually refer to as modified theory of gravity, which is basically something that we do in cosmology trying to account for the issues that we have in the standard cosmology. It's kind of an ambiguous definition what we want to do, because modified gravity is used for several things. One example, you can try to use modified gravity to account for the problems with the rotational orbits of galaxies. There are some kind of attempts to solve that problem without that part of modified gravity, but this is not what we're going to do. What we're going to talk about is modified gravity theories in the context of the accelerated expansion of the universe. How we can try to solve this issue without introducing any dark energy or cosmological constants. So to just recap a little bit what is the problem. So you know that from standard cosmology, one fundamental ingredient is general. You start from the action of general relativity that you can write down simply as what you probably got from the general relativity courses. You have the Lagrangian of the gravitational part plus some term that is related to the matter field, so the content. If you do the principle of minimal action within this Lagrangian, what you end up with is the Einstein equation. So you have the Einstein tensor that is defined this way. That is can be put equal to the stress energy tensor T. One note, I'm using C equal to 1 throughout all the lecture. So basically, you can go from this attraction to the Einstein equation, where you have a geometrical part, depending on the Ricci tensor and the Ricci scalar, and on the metric view, that is related by the theory of general relativity to the matter, to the content of the matter radiation that you put inside the stress energy. All right, so we got to this point of the equation of the Einstein equation. So if you want to apply this in the context of cosmology, what you usually do is you have to specify that. So we know that the universe is expanding, is isotropic homogeneous. So the metric that we usually refer to is the Friedmann metric. Robertson Walker, where the line element can be written in this way. So you have the time component, the scale factor, which is the fundamental, one of the fundamental ingredients of cosmology, which tells us how distances evolve with time. And here I'm neglecting the presence of to everything in a flat universe. So if you plug this equation, this metric inside the Einstein equation, this is a solution of the Einstein equation. And what you can get out of this, solving the different components, are the two Friedmann equations. So you have that, the first Friedmann equation, organized species, and the second Friedmann equation. All right, so you have these two Friedmann equations. The first one tells you how the scale factor evolves in the through time. So this is its derivative, which is connected to the Apple parameter H. And these can be connected to the species that you have in the universe. So the energy density of the different species, matter, radiation, and whatever you want to put in your universe here. The second term is something related instead to the variation of this rate of expansion, so the second derivative of A, which is related to the energy density and the pressure of the species. Okay? So what is the problem with this? This is all fantastic. The problem is that if you want to get an accelerated expansion, which is what we observe right now, you need to have that the pressure of some component is related to its density. So you need a very specific kind of component to drive an accelerated expansion. None of the standard components, so matter, radiation, curvature as well, satisfy this. So this means with the standard component that we have in the universe, there is no way to get an accelerated expansion. So how do you solve this problem? We observe the accelerated expansion. We need to find some way of positioning. There are two ways in which you can do that. Remember that all these parts comes from the Einstein equation, right? So you have two ways. You either introduce a new component inside your sense energy tensor property, or on the other hand, you modify this tensor, one of the two, correct? So what one usually does in standard cosmology is to introduce a new component, because cosmological constant, in which this relation is satisfied, because in a cosmological constant, you have the P is equal to minus rho. When you introduce lambda in your equation, it's something you have this satisfied. So this has a time and even range in time in which this can have a positive sign. The problem is, and this is needed to introduce a little bit what we're going to talk about to this lecture, what is lambda? Is a modification of the stress energy tensor, or is a modification of the geometric part of components of the universe? It can be both, because you can imagine to introduce a new component that has these properties here, whatever it is. Or one thing that you can do, you can just include that term minus lambda in your equation of general relativity, which is what actually Einstein did at the very beginning, to solve a completely different problem. But this came back as a possible solution. So this kind of already shows you that there is kind of ambiguity between what is dark energy, usually what we refer to dark energy is a new component that can drive the acceleration that is introduced here, and what is modified gravity, so modification of the distance. This is kind of very theoretical and vague for what is modified gravity, so let me show you a simple example. Erase here. So a simple example of modified gravity, the most simple modified gravity model the world can think about, is taking the equation, the action for general relativity, and just saying, okay, let's add a term, f of r. These are called f of r models. So we're basically saying, okay, in general relativity, we have just a simple linear dependence on this Ricci scalar, maybe it's different. What happens when you do this? You can do exactly the same thing you did before. So doing the principle of linear action, you will have a modified Einstein tensor that this time will depend on f and its derivative with respect to the Ricci scalar. I'm not writing it explicitly, but you can do that if you. And the other part is we're not touching the whole point. What happens if you do this is that you use again the Friedmann-Everett worker method, and what you obtain is a modified Friedmann equation. And writing it in terms of age, but you basically get so you basically see that with respect to the easy Friedmann equation that we had before, we have a bunch of new terms. All this part was not appearing before, and if you set your f to 0, you get that, right? So this is the first Friedmann equation. You can do the same thing with the second and write it down, but basically again, it will depend on the derivatives, on the shape of this function f that we didn't specify. This is whatever. So this means that in principle, what you can do is try to invent a new model, a function, decide, find the function in such a way that you solve the idioms. You will have some extra term with all kind of signs, you see, it depends on the derivative sign and so on, in such a way that you get an accelerated function without introducing any new model, new component. So you see that here what we did was to start from a modified Lagrange for gravity, changing this side of the Einstein equation, and get something that in principle will give us an accelerated. So it seems pretty straightforward that this is modified gravity. It's very different from this, right? Wrong, because it's not that straightforward. I will show you why. So in the context of general relativity, we usually distinguish between two cases, two frames. One that is called the Jordan frame, and one that is called the Einstein. What does it mean? It means that you can do a conformal transformation of your metric G. Basically, you can obtain a new metric just by a rotation of coordinates of the origins. So you start with this one, which gives you this particular Lagrange, and through a transformation, you can obtain a modifier. This means that in a different kind of metrics, all this quantity will change. Instead of R, you will have an R tilde that will depend on omega, and so on and so forth. So what can we do is to, if I choose, let me do this one. If I choose omega to be the derivative of the function, and then I just do a definition. I define a scalar field phi that is basically proportional to the logarithm of f of r. I'm just doing the definition. This is a scalar, this is a scalar, and just calling it phi to show what comes out next. You can do the calculation, and this is quite quick, but it can be done. You can check, you can see that with this transformation, this Lagrangian becomes this one, where you have integral x, well, I will remind tilde this time, and you have r tilde 16 by g minus no, I will go down here. You can move then the side, then the side. Then basically see that you can transform this equation where I have no fields, just everything is a tensor, a rich tensor, a rich scalar in this case. I can transform it by a simple change of coordinates in my metric into a Lagrangian that explicitly shows a scalar field. What is a scalar field? The new component that we're introducing. So again, I'm moving from something that is modified gravity to something that really looks like an incomplete. This is completely obvious. So this is what we usually refer to as the Jordan frame, while this is the Einstein frame. Why is it called the Einstein frame? Because the part that is tensorial looks exactly like that. Why is this important? It's important for one thing, what I was telling you, that tells you this ambiguity between modified gravity and dark energy, but also for another reason. The other reason is that, okay, so I'm looking at this one. This is a gravity, as I expect it to be. Plus, I have another fifth force, an extra force with respect to what we know, that is nowhere to be found in general relativity, right? What is the problem with this? The problem is that a fifth force needs to be detected. Instead, in solar system test, we always go in the lab, we have the weak force, some force, electromagnetism, and gravity. Where is this? So what you usually need to do is when you create your F1 model, you have to create it in such a way that when you do experiments here in the solar system, that it disappears completely. This is done by something that is called screening mechanism. So basically, you create a model that disappears when you don't need it to exist. And in F1 model, this is what is called a chameleon. So basically, if you treat these as a scalar field, you can see that the mass of this field is basically proportional to the derivative of this function. And so it means that when you create your F of r, you don't have to only pay attention to this creates an acceleration. Also, you have to create that this mass basically goes to infinity, becomes extremely large when we are in the space. Because an extremely large mass tells you that the force is very short distance. Maybe this happens. You cannot measure. While instead, when you go to cosmological scales, this has to be very tiny. So what one usually does is create this function in such a way that in high density environment here, the mass is large. When you go to low density environment of the universe, the mass is small. Any questions after we do? From a line from class? Otherwise, I push forward. Okay, so this is one simple example of modified gravity models. Modified gravity models are an incredible amount. I mean, people have been putting them up since we discovered the accelerated expansion. You have F of r that goes into the class of scalar tensor theories because there is a scalar and there is a tensor. You have pi gravity when you have two metrics coupled to each other, so all sorts of crazy things, higher dimension, whatever you want. So there is an incredible number of them. It's very tricky to measure. You cannot take a model, compare with observation, and see if it works, then to another, and so on, because it will take forever. So what one usually does is to use some kind of phenomenology. What it means is that you take the features of general relativity and try to see if you have a deviation, constraining them. This is done mostly not on the background, it's what now it's easy to see why you move the gravity, but on the evolution of cosmology. So the Friedman metric, when we do perturbations, is basically what we had before, but having some scalar perturbation. The metric is where so basically you have these two potentials that are tiny perturbations of the metric. These are quantities that change in space and time, and basically tell us how the universe is perturbed with respect to something homogeneous. We know that it needs to be perturbed because we have to create galaxies, planets, ourselves as well. So what you can do is solving the Einstein equation in this perturbed metric. You will get a part that is the homogeneous one that is before plus a perturbed part. But what matters is that when you do this, you can obtain equations that relate this potential to the density and to the density perturbation of the potential. These are what they are called the Poisson equation because they are the general relativity equivalent of Poisson equations. And they look like this. IG, delta, is squared.
Sir, can I ask a question? Swan?
Sure.
Yeah, so you have fixed the, say, conformal Newtonian gauge to get this, right? I mean, you have already fixed the gauge? Yeah.
Yeah, already fixed the gauge. You have some gauge freedom. Write down this equation, you have writing different gauges. So this metric can take different. I mean, you have some freedoms in writing this down. This is a specific choice that is much easier to write down this particular equation. But yes, you are correct. This is the Newtonian gauge. And it's called the Newtonian gauge because basically, if you look at the Newtonian limit, so the non-relativistic limit of this equation, these end up to be equation for your gravitational potential, the Newtonian relativity. So if you solve the Einstein equation in this context, you get this equation. You have an equation for psi, that as I was saying, using the Newtonian limit is just your standard gravitational potential. So it's what non-relativistic particle will feel as a potential when moving around in the universe. If you have a planet, a galaxy, they will feel this particular potential. You have an equation for phi plus psi. This instead is the equation, the Poisson equation that's relativistic particle. So this is the equation that determines how light is length by intervening path. And if you do all this in general relativity, you get this relation between the two potentials. So basically, you see that the two things becomes pretty much the same. Okay? So this is all in general relativity. I was telling you, in principle, you can take your FOR model or whatever unified gravity model you want to look at and try to work out these equations in that specific. You can do that for all the models you have, but this is quite unpractical. I actually forgot an A squared. It's quite unpractical because you have to do for many different ones. So what usually one does is to add some phenomenological function. Nu, omega k, sigma, k, and this becomes theta of A. So these are three functions. I don't know what they are. If they're equal to 1, it means I'm in general relativity. If they're different from 1, it means I'm not in general relativity. There is something that my model is not catching. So what I can do with this? Why is this useful? This is useful because this equation you see related to the density perturbation. This is related to delta, that is rho minus the average rho over the average rho. And these, basically, you can take them to create the matter power spectrum, which is related to basically all the observables that you can measure in the universe. CP, temperature is related to the correlation function of this quantity. Large scale fraction observables like gas, clustering, all these kind of things, everything is related to this one, understand the equation. So it means that if I'm modifying this equation, I'm modifying how it is. And I'm modifying what happens to my result. This means, for example, that if I work in f of r, I can define how this mu is written in an f of r model, compute my correlation function for delta, get prediction for CMB. How does CMB look like in f of r? And constrain the parameters of my f. Okay. However, if I'm being as general as this, I cannot do everything. So I can take this equation and plug them into some code that gives me the matter power spectrum or the CMB power spectrum, but I cannot put there a completely free function, right? So what one does is usually to create, or let me say something before moving on how we actually use this. So these three functions are not independent from each other. You can see basically these equations are basically combinable three equations. So it means that you can relate them sigma simply written like this. So you can choose which of the three you have as free and which is not free. And also one thing to understand a bit better how they work. Remember that this is the equation for non-relativistic particle, this is the equation for relativistic particle. So often these are called like mu, it's called like G matter over G Newtonian, while sigma is called G light over G Newtonian. So they are basically effective gravitational constants. What is the peculiarity is that we have two gravitational constants, one for matter and one for light. So we are violating what happens in general relativity, and matter and light couple the same way. So as I was saying, you can plug this equation somewhere in some software, but you can not use generic functions. So what usually one does is assume some parameterization. For example, one that is commonly used, you plug in something like mu is equal to 1 plus mu 0 omega of energy in sigma. So this is completely arbitrary, the choice that you do. The reason behind choosing something like this is that you have something that scales like omega energy, so in the past is negligible because you want the acceleration to happen now, so you know that it's going to happen now. And you have an amplitude with 0 and sigma 0 that tells you how much these functions that are deviating from 1, which is the general relativity. You plug them into your code and you can measure them. For example, with CMB, what the results that were obtained was something interesting at the time of Planck. Planck results gave us contours, confidence level contours that we will see later exactly what they are, mu and eta. This is the general relativity point, and they were finding something that looked like this. Slide here is when you have like 2 sigma of your probability, your general relativity point was 2 sigma. So might be that there is something not that significant in terms of statistics. All right. So to leave some room for questions for the end, let me recap a bit and then tell you the problems of this. So we saw F of R, basically in general, what modified gravity is used for. It creates an accelerated expansion. And we saw this approach. This approach is fantastic. It's used in many collaborations, experimental collaboration to constrain modified gravity, because it's general. I don't need to design a priori for this, right? So I plug in some parameterization, or if I want, for example, I can also write this in terms of my model. If I have my F of R model, I can write mu will become a function that is proportional to 1 plus the derivative of F. Sigma will be the same way. It's extra term that I'm writing. But it means that whatever model you choose, you can in principle map it into this format. So plug it into your code that implements this equation, and you're ready. You get your theoretical prediction, you compare with the experiment, you get your path. So this is a very powerful approach. It has some not so trivial problems. So first of all, as I was telling you, if you don't choose a specific model, you choose a parameterization that is completely arbitrary. You decide. Might be that this one doesn't catch any particular effect that is present in your theory. Because if you look, for example, mu versus redshift, this looks like something from 0 here. This looks like something like this. Maybe instead your theory does here stuff like this that you can never catch.
And then once you take that dumbbell off, you can then use your hand to push.
The other problem is the problem of no linearities. What do I mean with no linearities? The problem is that those equations that you saw in the Poisson equation with D, where D squared psi and so on and so forth, those assume that the perturbation of your field magnetics has moved. So it means that your density perturbation is lower. You are in linear regime. You can do everything in perturbation theory, so you can solve your equation. The problem is that at present time, we are definitely not in the linear regime. Perturbations are not small. We have galaxies, voids, clusters of galaxies, and so on and so forth. How this is solved? In lambda CDM, what you do is n-body simulation. You really do simulation of how things move. You get some fitting function, and you can work out how the linear regime looks, what the power spectrum is. Right? You cannot do that if you have general function. You cannot do a simulation for any mu and sigma, for any value of these parameters. This gets very expensive computation. It's very complicated. There are some attempts to solve this issue with like emulators or perturbation theory and stuff like this. But as far as I remember, since I started working on this like more than 10 years ago, this has been a problem. It's still, so we're still fighting. Another thing that is strange, let's say, in this approach is how you treat the data. So here I show you that mu and sigma parameterize the evolution of perturbation. I didn't say anything about these variables. Usually when you do this approach, you assume that your background evolves exactly as lambda CDM. So you basically put all the modification in the perturbation sector and say, okay, the background is lambda CDM. So observational piece is okay, because we know that it's very close, but there is no particular theory in which it's true. So it's kind of strange that you are completely separating the two things, perturbation. You look only at one. This can create some problems, for example, avoid the two detects. The final issue of this generic approach is the physical interpretation. So physical interpretation. Planck gives me this constraint. It tells me mu and sigma have to be inside this contour. And with 95% probability. What does it mean? What kind of theory is this? I have no way of knowing what kind of, if it's an f of r, if it's something more complicated, higher dimensional gravity, or not even modified gravity. If you remember, let me just write this one. A squared c, this was proportional to g, mu, a squared, log delta. This comes from the evolution of matter. So it might be that here I'm saying, oh, this mu that I'm detecting is modified gravity, but actually it's just the matter is a different extent. The problem of being general is that you can confuse one effect. So this is a very powerful approach, it's still used, but people are trying to overcome this, trying to find something that is a little bit more general, but at the same way you can interpret more from the physical. And one of these, I will not tell you anything about that, but I just want to mention what is called the EFT of dark energy molecular gravity. That doesn't work in this way. Here we are parameterizing deviation from the observation. What you do in this case, which is much more complicated, is to parameterize deviation from the action of the relativity. So what you do, instead of writing S as the integral PR16 G, you start adding all sorts of functions, usually expressed in terms of some alpha, alpha m, alpha t, and so on and so forth. There are parameterization of deviation from the action. So you're not parameterizing the effects that you have on the observable, but directly the field. This is more complicated to handle, but much more easier to interpret. Yes. And in the notes of the lecture, I have some links if you're interested in these, or you can write if you want. So I was told from online, leave some room for questions before switching to the next lecture. So any question from the room or any question online?
Sir, could you just take what is the effective field theory? Like, what is the plus sign? I could not read. I mean, is it the C or what?
Sorry, say again?
Yeah. What is the EFT written? I mean, plus I cannot see from here actually. Oh, that is.
I wrote it just qualitatively. So what you have in the effective field theory is just that you parameterize. Other than this, you basically have some function of some quantities that are usually alpha m, alpha t, alpha k, and alpha b. So basically, these are functions that parameterize alpha m is how the Planck mass changes with time, for example. Alpha t parameterizes the difference between the speed of the gravitational waves and the speed of light. Alpha k is a kineticity term related basically to the kinetic term of the scalar field that you usually can arrange in the Einstein frame. Alpha b is a grading term, and it's something complicated and very difficult to describe physically, but it's another term that basically you can put it here. You can write the equation in terms of this function here. And this basically allows you to identify, for example, is only alpha m different from 0, then it means I have a change in the Planck mass, I have a change of the gravitational constant. This is quite of interest because this is something that we concentrate very strongly with observations. Because with the measurement of gravitational waves, speed of electromagnetic counterpart, what we got is that the two speed of light and speed of gravitational wave, is the same. So this would basically tell us, okay, alpha t equals 0. And this would kill a huge amount of modified gravity theories. So putting it in this way really helps you to give some physical meaning at the kind of gravitation of modified gravity theory that you're looking at. Here I'm not writing it explicitly, but if you look for the EFT of the energy modified gravity, it's usually indicated like this. There is quite some literature on this. There is also a code, a modification of the CAM code, which is a EFT CAM, or you have high class, so you have two modes that deal with this particular approach. And they can give you theoretical prediction or a bunch of observables in this particular field. So you can play to see how it changes.
Yes, sir. Actually, what I was wondering that in quantum field theory, the effective field theories are the one where you cut off by some lambda and you take how should I say, infrared, what is the level of quantum field theory, right? For example, Salam-Glasgow effective field theory would be say Fermi-weak interaction. So I am asking that here, where do you put the cutoff mass? I mean, like your cutoff would be based on the Hubble horizon or like the other. So that's what I was wondering, that in the beta function, at least, like do you particularly put a cutoff based on the particle physics, or is it a graviton-graviton interaction, just like the R square can be done by the one loop correction of graviton? So that's what I am wondering, that what is the QFT origin of EFT?
So in this sense, if you want, the effective field theory name is a bit of a stretch, because it's not really that formally well done. There is a cutoff mass, indeed, in terms of the scale of energy that you're looking at. Here you are really in the infrared, right? Because you are interested only in something that happens at the level of the gravity that is not so strong, because you are in the late universe, so you are not like close to a black hole or something like that. There is no idea that this thing is a completion of like an effective theory of a quantum gravity approach. This is just a way of treating the problem in a way that is similar to how you usually work with effective theories. It's not really that formally connected to a effective theory in the real sense of the word. It's been called like this mostly because it's inspired. So it's not that straightforward to answer your question in the sense, I don't know what is this.
Okay. No, because people call that FR gravity as an effective field theory of a gravity because the gate calls. So that's what I was wondering.
Okay. No.
I mean, FR, yeah. Yeah.
So I just wanted to ask, is there a way to connect the EFT formalism to the mu sigma formalism somehow? So I guess the EFT is like more general because you're modifying the action. So I was wondering, can we reduce it to mu sigma somehow or not? Thanks.
You can in some cases, in the sense that to get an analytical correspondence between mu and sigma and the alphas or whatever way you work with the effective theory, you can do that. But you can do that only under some assumptions. For example, what is called the quasi-static approximation, where you basically assume that your potential and psi vary very slowly, so you can reflect some derivatives. In that case, you can do really a straightforward connection one to the other. Otherwise, things are quite complicated. You have to do it numerically, but yes, there is a correspondence, because in the end, you're kind of looking at the same things. One thing, if I remember correctly, but I'm not 100% sure of this, you cannot do that for alpha k. Alpha k is something that is kind of elusive at the observational level. Your observation weekly depends on this, and if I remember correctly, you really don't see it appearing anywhere in your equations. But in principle, under some assumption, you can do what you want.
Sorry for the question.
Yeah.
These theories can be related with the Ordesky theories?
The effective field theory, this particular approach, is done for scalar tensor theories, so like FOBAR that we were discussing before, which fall under the Ordesky class. So the Ordesky class, for who don't know the definition, is the class of more general class of theory that is scalar tensor. So the Euler Lagrangian contains a tensor part and a scalar part. FOBAR is one example, but you can do that in many other ways. And the Ordesky class is exactly what is looked at in this effective. This formulation here doesn't go for all models. It's just for that particular case. So indeed, this is limited to the Ordesky part.
Okay, thank you.
All right. So as I was saying before we started the other lecture, this is completely. So up to now we saw some specific models of irregularity and so on. now the topic of this lecture is what do we do when we have data. So we have organized models, also understand, moving gravity, dark energy, whatever. We want to understand how we can illustrate it with data. Okay? I take a very general approach in this, in the sense that I'm just looking at the statistics that we're going to do, not really looking at any particular. So the question that we want to answer is one. We have a set of data, whatever cosmological observations you like, and we want to estimate the parameter. We want to know, for example, how much is mu zero, how much is h naught, what is the value of that. So basically, to formalize a little bit the problem, you have a set of data, X, particularly creative as a you have a model M in which you are trying to investigate, lambda CM, for example, and this model M have a set of parameters. You want to estimate these parameters. So you know what is their mean values, what is their uncertainty, you know the uncertainty that you have on the data. So basically what you want with this set of things, what you want to estimate is the probability distribution of your parameters given your data. So a conditional probability, right? Fantastic. But if we have a set of data and a given model, we cannot compute the metrics. What we can compute, I mean, if you use a frequentist approach, you can do experiments, you can do your experiment over and over and over, you get different quantities, different data, and you get a construct. In cosmology, we cannot do experiments. There is this problem. You have to look up, you have a set of data and see. That is the data you do. So what you will do is you have one set of data, you set of parameters. What you can easily compute is not that, but rather this one. The probability of the data given the value of your parameter. So you say, I have a model, lambda CDM. I select the values of the different parameters that are in there. I take my data, what is the probability that I get exactly this data from my data? This you can compute. When you have a set of data, you can compute this. But it's not what you're interested in. You want the other thing. In order to get from this to this, you use what is the bias theorem. Okay, never understood those concepts. The theorem tells you that the probability of the parameters given the data, which is basic statistics, the joint probability of the two, can be written as E yes. You can write this probability in this way. So this means that the thing that I could compute easily when I get some data, this probability is called likelihood. So the likelihood that I get some data is related to the probability of my parameter, which is called posterior. The likelihood. The two are related by a quantity that is the prior, so the probability of having some values of the parameter, we will look at this later, and the evidence. That is basically a normalization. This is a probability that to integrate, if you integrate this over all the values of the parameter, it has to be one, right? So this is basically just a normalization. Not really, because we will see later if we have time that this is quite useful for some things that are called model selection. So This is what we said we can compute this, correct? This is the likelihood probability, is the probability of your data, given the parameters. You usually do some assumption. For example, usually you assume that this is that your data are Gaussian distributed. So, for example, you can find here wrong. Your likelihood is usually written something like the logarithm. Let me drop the vector field because I don't like the weather. So if this is proportional, if you assume that the data are Gaussian distributed, this is just so basically, you assume that your data are Gaussian distributed in the sense that you can compute the difference between what you get and what you expect, given a certain parameter, and you can compute the probability. This is a Gaussian probability, where basically you see that it's the covariance matrix, you have the error from your experiment. So here you have your measurement error come out when you observe. So this is something that I was saying you can easily do. What are these other two things? These, as I was saying, these are normalization. So basically, you want to ensure that here is here because I need the here. You basically want to ensure that this integral of p theta x theta is equal to 1. Integrate over the 1. And this basically you can do the calculation with the bias theorem, and this tells you that p of x is simply the integral of p x theta theta. So as I was saying, this is simply a normalization. It's the integral of the posterior over all your parameters. Easy. What is this thing? This is called prior, for one reason. Basically encodes all the prior knowledge that you have of the parameters, which is clear because we are trying to vector. Right? So this means that in this quantity here, everything that you know already can be something that comes from other experiments, something that comes from theory as well. To make an example, let's say that my data X are can be measurements, for example, but I want to include the information that I get on H naught, the hour constant from supernova. How do I do that? I can simply say P of H naught is proportional to the exponent because it's Gaussian. H naught is H naught. What am I doing here? I'm basically computing the probability of H naught given some measure. This is HF is my measure that comes to supernova, which comes with an error. I take this probability and I multiply for the difference. And this basically tells me if my likely wants, I don't know, H naught equal to 50, but my measurement before say no, H naught is 70 plus minus 1, this will avoid that my posterior distribution will go to 50. So basically, if you want to visualize it, what you have is that this is your H naught. You will have your data that will give you, for example, some distribution like this for H naught. And your prior, there is something like this. If you multiply the two, you will get something in the middle. Okay? So you are combining two information. If these two are too far away, when you multiply them, you get Z, right? So this is telling you there is something wrong, and there's some weird mistake in my measurement. Another example of how this prior distribution can be used is to include some theoretical information. To make a very stupid example, let's say you are measuring the neutrino mass with CB. You can do that. You can measure the sum of neutrino masses using CB, and you want to measure that, but you have some theoretical value. What is this theoretical value? That the sum of the neutrino masses has to be higher than Z, right? Or equal, if you want. It cannot be negative, the sum of masses, correct? So basically, you can include this information in there by just saying, oh, P or sum of the neutrino masses is proportional to an heaviside theta of something. You multiply this by the largitude, and this is automatically reduced. Okay, so this is if you have some prior information on your parameters, but it might not be the case. It might be that you don't have nothing. For example, the modified time in the CD form, we don't have much. So what you can use is basically what is called an informative time. You give it a range, like it cannot be lower than 0, but it can be whatever. So what you use is a flat prime. You're just saying, okay, my prime is flat. And to go back to that plot I was showing before, this is your likelihood, probability, or probability you get from your data, you run it from the prime. Basically tells you, yeah, okay, whatever your data tell you, fine. Okay, this basically was to explain a little bit how you get from your data formally to your posterior distribution. This is what we want to measure. Why do we want to measure this? We want to measure this because, as I was saying at the beginning, we want to estimate these things, right? How do we estimate? We need to find estimators of our parameter, and there are many ways to do so. For example, if your likelihood is Gaussian, your prior is an informative, so it means that if the posterior is just proportional to the prior, one thing that you can define is what is called the maximum likelihood estimation. So you can find theta, this, where it's just defined as the maximum over theta of your likelihood function. Let me call it there. When we get confused. Likely. So this is a possible estimation. I take my probability distribution, I take the peak, and say this is the value. Most probable, most likely value. This obviously changes if you have a prior that is informative, because the peak of your likelihood will not be the peak of the state. So things get a little. So what one usually prefers doing, and this if you look at whatever paper for a collaboration, someone that constrains a particular model, they never quote this. This value is never quoted. What they quote is the mean value of them. So basically, the estimator is just the integral over the theta x. Just the definition of a mean value given a probability distribution. This is what we usually get into papers, because it's the most reasonable thing that we want to do. The problem, what is the problem? Is that this is a mean for all the parameters. These are all vectors, right? Usually you want this parameter by parameter. What is the value of H0? What is the value of W, omega bar? So what you have to do is something that is called marginalization. Marginalization means that you want to find the posterior distribution of one single parameter, p theta 1. And this, if you have your posterior, is simply done by integrating overall the other parameter to n, your posterior distribution. Overall the possible one. So you have a distribution, you integrate all the parameters you are not interested in, you don't care about those, you get the posterior distribution for a single. Okay, and you can get the real value. And this means that if you want, from this marginalized posterior distribution, you can also get some balance, in the sense that when you do the experiments, you're not interested just in the value, you want to have some errors, right? This parameter can go from here to here. H naught is 67 plus minus 0.5. This, if you have this quantity in n, it's easy to find because you basically have to find the theta minimum and theta maximum. It basically gives you some probability. Example for 1 sigma Gaussian, this you will see, yes. You have to find the theta minimum and theta maximum, for which you have 68% of the probability. So you say, my value of theta 1 will be a given value plus something minus something. It has to be inside here, values as this one, will basically characterize completely your parameters. One other thing that you can do is that if you have, instead of a posterior on a single parameter, but a posterior on two, so let's say theta 1 and theta 2, you get a two-dimensional distribution, and you can get some confidence level contours. For example, you can integrate and find the value of theta 1 and theta 2, they give you the 68%, and you find those nice contours that I showed you before. And you can do it for whatever level of probability you want, 68%, 95%, 7%. Okay, so basically if we have this posterior thing in n, which we can get in principle from the library, we can do all these fantastic stuff. And correlation between parameters, values, ranges, integrating out things, and so on. How do we get this practically? Because this is the tricky part. Everything that we did up now is basic statistics, but we have somehow to get this function out of your data. So this is where things get tricky. Because, like, if you have only two parameters, for example, theta 1 and theta 2 only in this vector, things are easy. You can do what is called a grid search. You take one value of theta 1, one value of theta 2, compute this, multiply this. Then change the value of one parameter, go ahead, so on and so forth. For two parameters, it's easy. You really just do kind of a grid and compute your posterior distribution here, 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 and so on, and you get some sort of two. But what if you have 3, 4, 5, 10 parameters? Like lambda SVM, its minimal form is 6. Already we cannot do this because things scale very badly with the number. So what one does, and this is the simplest approach that we can have, and there are some more complicated ones, is what is called a Monte Carlo approach. Actually, the bias here because I need it. So you do what is called a Monte Carlo approach. What is this? So basically you want to move in your parameter space, but not automatically. You want to find some algorithms that puts you in the place that are interested. You evaluate this posterior distribution only where you need, so that you can limit the number of times that you need. It's called this way because it takes a random drawing of the parameter space. And it works like a Markov process, in which each time you move, your movement only depends on the step before and completely forgets what happened. So each step is related only to the one immediately, the Markov process. I will show you one particular algorithm. It is called Metropolis Hastings. And works like this. Step one, you choose a starting point. It is arbitrary. You decide where you start. You put there values of your parameter, H naught is 50, omega factor is 1, whatever you want. You start with it. And you compute E equals 0 x. So given the Bayes theorem, which is beta 0, parameter, compute. Nice. Second step. I move from theta 0 to another theta 1. How do I do that? Usually this is done taking a normal distribution. So you're just proportional to exponent. So you basically are seeking in theta 0. Theta 0 is the mean of your Gaussian distribution, and you extract a point from this probability randomly. You move to a theta 1 that is inside this distribution. Sigma p tells you how wide is this probability, how much you want to move. This is a parameter that you have to choose. So you really have a choice to do. Where you start, how much you move. And this I will explain a little bit what it is. Okay, we went from theta 0 to a given theta 1 that we extract from here. Theta 1. If we extract a value of theta 1, we can also compute the posterior distribution of theta 1. Right? Okay, so now we have one step and another one. So what we can do is compute the ratio of the P theta 1, Px, P theta 0, x. Okay, just the ratio of the two posterior distances. This already tells you why I was saying that the evidence is not important. This doesn't change with the values of the parameter. So if I take this ratio here, the thing goes away. I don't have to compute it. I take this ratio, and what does it tell me? We have two cases. One case, A is our higher than 1. What does it mean? It means that moving from theta 0 to theta 1, I'm moving towards the peak of the distribution. Right? So this is a good movement. I'm going to find where is my peak. I'm going towards the highest probability if this ratio is higher. So I want to keep that. If we are in this case, A higher than 1, I move from theta 0 to theta 1 if what is called I'm accepting the point. It means I'm starting to construct a chain. My first part of the chain is theta 0, parameter 1, theta 0, parameter 2, and so on and so forth. If I accept this theta 1, it means on my file that I'm writing, I write another one, theta 1, theta 2, and so on and so forth. Okay, I'm accepting the point. The other case, A is lower than. It means that the probability when I'm in this theta 1 is lower than. So naively, I would say, okay, then I discovered I would like it. But if I do just this, the only thing that I'm doing is doing a maximization algorithm. I'm looking for the peak. I'm not doing that. I want to reconstruct the full posterior distribution. So sometimes accepting this point is also possible. And now when you decide, you basically extract a random value, R. uniformly distributed between 0 and 1. If R is lower than A, you accept the point derivative. So the point is worse, but I'm accepting anyway because it satisfies the condition. Why this condition? Because if this value is very, very low, so this point is much, much worse than the other, this is very difficult. So you're not going to work very, very, very close. I'm keeping it if it's bad, but not so. So what I do now? In case I accept the point, θ1 goes in my chain, and I repeat exactly the same thing, just starting from θ1. You have to decide again. I take θ1 as a new starting point, and I go ahead, compute θ2, do the ratio, if I reject the point, so this relation is not satisfying, I discard θ1. I don't keep it in my chain, and I go back, restart from θ0. Take another point until I find something. Why do we do this approach? Basically, can be shown that if you let this thing going on long enough, the density of your points in a given region omega, you take a region of the parameter space and look at the density of the point in the region that you got in this chain, is proportional to the integral of omega of your posterior distribution. So you're basically reconstructing the density of points that tells me how this works. If I let the chain go long enough. There is an algorithm to compute what long enough means, because you always have to normalize that. It's called the Heidelberg statistics, but I'm not going to that for the sake of time. But basically, what it tells you, it basically checks two things. You can do this in one chain, so that's one thing, starting point at 0 and go forward, but you can do that many times. For example, I can use 4 different chains with different starting points that go independently for the chain. So these gamma-rupin statistics look at the variance within the chain and the variance chain to chain that you get on your parameters. And when the chains converge together and they do the same thing, they say, okay, I got it. And it's stable enough, the algorithms converge, you have reached this particular condition. And basically it means that looking into dimensions, you get a bunch of points around, they are basically concentrated exactly as your possibilities. Okay? All right, so to do this approach, now basically with this approach, you get your distribution. You're good, you can do whatever I was telling you before. Actually, some things are much, much more easier than before, because for example, to do marginalization, I don't even have to do anything. Can be shown that the marginalization, for example, if I want to remove θ2, I want to marginalize out θ2, it's enough to take my file, remove this column, and marginalize. I don't have to do anything. It's easy. This is very nice, but it has some problems. What are the problems and the limitation of this algorithm? Mainly two. And it's mainly related to those quantities that you have to decide a priori. So you have to decide the starting point in 0. You have to decide the weight of your proposal distribution. So how you move from one to another. Why this can be a problem? Well, let's take again θ1 and θ2 here. And let's say this is our target distribution. This is the distribution of one of these. Right? This is a section. With these being the link. So if I take θ0 here, my algorithm will go around and do some this. What if I take θ0 here? I know nothing about periodical distributions. I can mess it up how much I want. The algorithm will converge anyway. Very slow. So you will start moving around here, then sooner or later you will start to do this, and in the end you will start sampling around it. This is what is called, this part is called Barnum phase. And it's basically the MCHC trying to fix the mistake that you did by itself. To avoid problems, because remember, what you want to look at here is the density of points on a given region. To avoid problems, what one usually does when you construct your chain, you take the first 20, 30% of your chain and you throw it out. So you discard some points because you know that by the starting point, it's a mess. Even if you got it correctly, you discard it anyway. Because anyway, if you are correct, you are still hanging around and your process is stable. So this is what it's the Barnum. It can really slow you down. And actually, connecting to this one, it can also create other kind of problems. Because let's see at that sigma. Let's do it in one dimension because it's easy. So let's say this is logarithm of probability, the Cauchy distribution, and this is my only parameter. And let's say that the minus log of my probability looks something like this, very high. And this is my theta zero. HOZ. Okay? Now what happens if I mess up sigma p? So if I get, it will flatten out. So if I take a too large sigma p, it means that the Gaussian from which I sample my next point, if sigma p is too wide, it means that my movement will start to be something like this. This is my next point, this is my next point, starting to move this way, and I will never fall exactly, it will just be a line. The problem with a too small sigma p is that I start doing very tiny steps. You do this, and I start to bounce. For example, if there is a secondary minimum, there is the risk that I get stuck inside. So, for example, I leave the chain going for a while, my gamma statistic tells me, maybe only one, yeah, you're good, you have converged. I converge to this, well, the peak was here. So one has to be very careful, and that's why you usually do more than one chain, because this starting point might get stuck, and if you get this other starting point, it doesn't. So if you do two different chains to then compare, this will happen. Also, this tells you another thing. In Metropolis Astic, this algorithm is not very good when you have a probability distribution that is more than one. So if for any reason, it's difficult to see something like that in cosmology. But if for one reason you have a probability distribution that looks something like this, maybe your MCLC gets inside, gets stuck here, and never explodes. For this reason, there is some more complicated thing that you can do, some different sampling techniques that, for example, can overcome this issue. One of them is what is called nested sampling. Nested sampling, I will not show the algorithm, but the philosophy is that if you have a private volume, so this is the range allowed for your parameters, we'll start with sample anywhere in this private. So we'll take some points around, then exclude the less likely ones and draw up on two. Then sample again inside, exclude the less likely ones, and draw up on two until you converge. And you can be sure that if you have two peaks, it will show you two peaks. Okay, any question on this? I hear it now. So, okay, in these last few minutes, I will try to show why do we keep this data? Why do we keep the evidence there? Since we never used it now. So this is what we want, all of that we saw up to now, what to do for parameter distinction. Given one model that you assume is true, and that's an assumption, you can use all this technique and measure the parameter. How do you know if your assumption that the model is true is correct? How do you compare two models? This is what is called model selection, in which instead of being interested in this probability, we are basically interested in this, the probability of the model given the data. All right? What we can do is we use again the bias theorem here as well. You know, it's the same. So the probability of X given the model, probability of the model, and proportion. Right? But what is this quantity? Here I'm changing a bit the notation, but the probability of X given the model, it means the probability of the data, whatever is the value of the parameter of the model before. So it's the integral in theta of Px theta multiplied by the prime. Is my evidence, it's exactly the objective, the normalization of this quantity. So what it means is that if you want to compare two models, you can take the ratio of their probability. So what you can do is take E model 2 X, E model 1 X, and if you use this approach, you basically have this E model 2, E model 1, integral is objective. You have to write it, it's theta, let's write it as a posterior of theta 2, X, so you basically have a ratio of the integral of the posterior times the prior probability of the root. So this means if you have any reason to believe one model more than the other, you can include it in here. But usually this is not the case. You usually say, okay, the models have the same probability. So what you end up with, and I will write it explicitly, is what is called the bias ratio. The bias ratio is basically the ratio of those two integrals. That writing it in terms of the likelihood, basically the integral likelihood of X over theta given model 1, model 2, sorry, times the prior of the parameters of model 2, and the same thing for this is what is called the bias ratio. You take the two and it gives you quite some information. Because one question that one can ask is, why am I doing this? Can I not just look at the peak of the two distribution? What gives me the highest likelihood, the highest probability of the two? The chi-square. If I look simply at the chi-square of the data in the model 2 and the chi-square of the data in the model 1, I have one model that gives me a lower chi-square, more likely a better. To explain that. One thing that looking only at the chi-square doesn't give you is account for the complexity of it. If you have a model with 6 parameters, and if you have a model with 100 parameters, the one with 100 will always have a better chi-square. If you have enough parameters, you can fit whatever you want. This, this integral over the parameter space given the value accounts for the prior model. It basically tells you what accounts both for the goodness of fit and the complexity of it. So you have one term that supports whatever fits the data better, and one term that supports whatever is simple. In fact, if you have two nested models, so first let's do this. We can rewrite this one. Let's see that the prior of my parameters is only good. So I just have a range for it. I have n parameters for one model and then prime for the other. So basically, I remove one. And if this is just a range, basically you have this integral, and then you have the ratio of theta 1, theta 1, and theta 1, theta 2, and prime. Basically, theta 2, the lower 2 indicates that is for model 2, 1 indicates that is for 2. And then each of the model has a given number. So basically, you can write like this. This part tells you how good is your model fitting the data. This one tells you how big it's made, how complex. And this can be seen if I have a nested model. Nested model will mean that M2 is included inside M1. So let's say that model 1 has n parameters that are equal to the model 2 until n prime. And then it has some more. So let's say that we basically go from n prime to n, they are exclusive of this model, all the other ones are on top. If you take this ratio, the priors will be the same, you basically see that this can be written as delta and prime plus 1 all the way up to n. And you see that this is something that is positive, I have the 1 that multiplies this product. So we always push the bias ratio toward preferring model. The simplest model is always. And this is basically how, for example, you can compare my modified gravity models from before with understand. A modified gravity model is better liked by the data, but it has some extra parameters. Does it work better than understand enough to justify these extra parameters? And this is maybe what you can do the evidence that is the you have to compute. This way you can extract from your postulates. And since we have 5 minutes left, I will stop here. There is another part on the notes on how you compute agreement within data set and so on, but it's here if you want to read it. It's there. I will stop here and take questions from the room, or from online.
Yeah, sir, thank you very much for this amazing talk, like both the observation and theory. So if I understand correctly, like at the end of the day, in the Bayesian one, you want to find a maxima or like the minima with the minus log, right? I mean, the likelihood of this. My understanding of this Bayesian analysis is that you are trying to find the maxima or the minima in this case because of likelihood, right? So you are proposing like various algorithms. For example, metropolis testing you have already talked.
So here the point is not really finding the maximum or not. You want to reconstruct really the full distribution. Because if you only have to find the maximum, you don't need all this thing of the metropolis aspects. You can use much simpler minimization algorithm and just look at the values of the parameter that minimize your K-square. The idea of using all these complex machinery is that you reconstruct the full posterior distribution. Because this way you have many phase. Metropolis aspects is one way, and it's the simplest one, but it's definitely not the only one. There are many different possibilities. There are some things that I touched on nested sampling, but there are more complex things like Hamiltonian Monte Carlo, in which you start to take the derivative of your posterior distribution, and you basically decide this way how to move around your function space. It's really not just a minimization or maximization problem. It really depends on an extended.
Yeah, so that's what I was asking, that what about the convergence of it? Like, I mean, if I change for even, let's say, even for metropolis testing, so if I change from Gaussian to some Poisson distribution, would the convergence help a little bit? Like, can I reach to close to likelihood maxima or minima little faster or slower, or is it like a distribution independent?
No, it's definitely not distribution independent. It really depends on what you're looking at. As I was showing you before, if you have something that is like double peaked, it's really complicated to use metropolis assets. You really, the efficiency really depends on the distribution that you want to obtain at the end. The problem is that you don't know this distribution from start. So it's a trial and error thing. It's really difficult to choose the most adapt algorithm upload. You have to try, fail horribly, and then start again with the one.
Okay, thank you, sir. Yeah.
I see a question on the chat. How strongly will the algorithm depends on the choice of priors? For example, if instead of Gaussian, we take a flat prior when comparing two models. As long as the posterior, no, it depends on that. In the sense that a good prior, for example, a Gaussian prior really forces you to be close to the peak. So your algorithm will be more efficient, because whenever you try to stray away from that, the prior will kill that point and bring you back in the place where you are. If you have an informative priors, you pretty much wouldn't go anywhere. So for example, if your starting point is very bad, but your prior is strong, you will notice it. If instead you don't have an informative prior, you can go around the parameter space for a while before you actually find something. I hope this answers to the question.
Okay, thank you, Matteo, very much for the nice lectures.